Our sources today are pretty technical.
They are.
We have course notes called High Performance Physics, and we also have the actual computer code for a game engine called the Titan engine.
So this is the real deal.
This is the real deal. These sources are usually for experts, but our job today is to translate them. We're going to turn them into simple concepts that anyone can understand.
Okay, let's start with the big picture then. What is the problem we are trying to solve today?
The problem is time.
Time.
Specifically, the problem is that we do not have enough of it.
When I play a video game, it feels smooth.
Yeah.
It looks like a movie. I see a character running or a car driving, and it all looks continuous.
That's an illusion, a very clever
Like
illusion.
an illusion.
Yes, a video game is not continuous at all. It is a series of still pictures. We call these pictures frames.
Okay.
The computer draws one picture, then it quickly draws another, then another. If it does this fast enough, your brain thinks it's seeing movement.
We often hear the term 60 FPS. What does that mean exactly?
FPS stands for frames per second. So 60 FPS means the computer must draw 60 separate pictures every single second.
60 times a second. That sounds very fast.
It is fast,
Yeah.
but let's look at the math. Let's figure out exactly how much time the computer has to draw one of those pictures.
Okay, let's do the calculation. So 1 second, that's equal to 1,000 milliseconds.
Correct. So we take those 1,000 milliseconds and we divide it by 60 frames.
1,000 divided by 60, that is, let me think, roughly 16.6.
Exactly. Let's just round it down to 16 to be safe. That is our deadline. 16 milliseconds.
16 milliseconds.
Every time the clock ticks inside the computer, it has exactly 16 milliseconds to do all its work.
When you say all its work, what does that include? It's not just drawing the picture, is it?
No, not at all. Drawing the picture is actually the very last step. Before it can draw anything, it has to do 3 other big jobs.
Okay, what's the first one?
First, it has to read the input. Did you move the mouse? Did you press a key on the keyboard?
That seems simple enough.
Second, it has to update the game rules. Did your character pick up a coin? Did a monster see you? Did you win the level?
Okay, so game logic.
Right. And third, and this is the hardest part, the focus of today, it must simulate physics.
Right.
Imagine a space game. You have 10,000 asteroids flying around in space. The computer has to look at every single one of those asteroids.
Everyone.
Every single one. It has to figure out where that asteroid moves next. It has to check, did this asteroid hit another asteroid? Did it hit the player's ship?
And it has to do that for 10,000 objects.
Yes. And it has to do all of that, plus the input, plus the game rules, in less than 16 milliseconds.
What happens if it takes too long?
Yeah.
What if the computer takes, say, 17 milliseconds?
Then you miss the deadline. And the screen doesn't update. The game freezes for a tiny moment. We call this a stutter.
Oh, I've seen that. I hate that.
Everyone hates it. If you're playing a fast racing game and the game stutters right before a turn, you might crash your car. It feels bad. It ruins the fun.
So speed is everything. We need to be extremely, extremely fast.
Exactly. And this leads us to our first big technical lesson, the difference between scalar and vector.
Scalar and vector. Okay, those sound like math words. Can we explain them simply?
Yes. To understand this, we need to understand how the brain of the computer works. The brain is called the CPU.
Right. I usually imagine the CPU and the memory, the RAM, are kind of the same thing. They're all inside the computer case.
Physically, yes, they are in the same case, but electronically, they are very, very far apart.
How far?
Well, I like to use an analogy. Imagine you are working in an office. You're sitting at a desk. That desk is the CPU.
I'm at my desk.
The memory, the RAM, is a library. But the library is not in your office. It's not even in your building. The library is down the street.
That is far away.
It is. Now, imagine you want to add 2 numbers together. But the numbers are written in books in that library. You can't do the math while the books are still in the library.
No, I have to go get them.
You have to go get them. So you have to stand up, walk out of your office, walk down the street, go into the library, find the right book, check it out, and walk all the way back to your desk.
Oh.
Only when the book is on your desk can you open it, read the number, and finally do the math. Your desk is what we call a register.
A register.
A register is a tiny, super fast storage space right inside the CPU. It is the only place where the computer can actually calculate things.
Okay, so RAM is the library way down the street.
Huh.
The register is the desk right in front of me.
Perfect. Now let's look at the old way of doing math. We call this scalar mode. The technical name is SISD.
What does that stand for?
Single instruction, single data. It basically means do one thing to one number.
Let's walk through an example. We have our asteroid. We want to move it. To locate the asteroid in 3D space, we use three numbers, x, y, and z.
Correct.
X is left and right, y is up and down, and z is forward and backward.
Right. And the asteroid also has speed. It has speed x, speed y, and speed z.
Okay.
To move the asteroid, we need to add the speed to the position. So position x plus speed x, position y plus speed y, and position z plus speed z.
Right. So in the old way, the scalar way, how does the CPU do this?
Oh, it's very painful. It's a lot of walking.
Okay, step one.
Step 1, you walk to the library, you get the book that has the number for position x, you bring it back to your desk.
Okay, I have position x.
Step 2, you walk all the way back to the library, you get the book for speed x, you bring it back to your desk.
Right.
Step 3, now that both numbers are on your desk, you can finally add them together.
That is a lot of walking just for the x value.
And you are not done. Now you have to do the exact same thing for y.
Oh, no.
Walk to the library, get position y, walk back, walk to the library again, get speed y, add them, and then you have to do it all over again for z.
That seems incredibly slow. I feel like I'm spending all my time walking to and from the library. I'm not spending much time actually doing math.
That's the first problem. It's slow. But there is another, maybe even bigger problem. It's wasteful.
Graceful. How?
The course notes mention a huge problem with the registers, with the desk.
What's the problem with the desk?
Modern computers have big desks. A modern register is 128 bits wide.
128 bits. Is that big?
Well, let's compare it to our number. A single number for position x is usually 32 bits.
Ah, I see. The desk is 128 bits wide, but the number I'm putting on it is only 32 bits.
Exactly. Imagine you have a giant shipping crate. It's big enough to hold 4 large suitcases,
Okay.
but you only put one small handbag inside it, and then you seal it up and ship it.
The rest of the crate is just empty, full of air.
Yes, it's filled with air. In the computer chip, those empty bits are physically made of silicon. They are electrical circuits, they have power running to them.
And they're doing nothing.
Nothing. When we use scalar mode, those circuits are just sitting there, powered on, doing absolutely nothing. We are using less than 25% of the computer's power.
That's terrible. So we're wasting time walking to the library, and we're wasting space in the crate.
Exactly. So how do we fix this?
I'm guessing we use the vector method?
We use the vector method. The technical name is SIMD.
SIMD. What does that stand for?
Single instruction, multiple data.
Multiple data. That sounds like the solution right there.
It is. Instead of treating x, y, and z as 3 separate numbers, we basically glue them together.
Okay.
We pack them all into one crate. Because 128 divided by 32 is 4, we can fit exactly 4 numbers in the register at the same time.
So we put X, Y, and Z in the crate. That's 3 numbers. We still have room for one more.
We do. We usually add a dummy number, often called W, just to fill up the space. So now our crate contains 4 numbers, X, Y, Z, W.
Okay, we filled the crate. We bring it to the desk in one trip, which is faster. But how does that help with the addition? Can the computer add a whole crate at once?
Yes. This is the magic. This is the revolution.
Really?
The CPU is smart. It has 4 little calculator circuits inside it, all wired up to work together. When we give the command add, all 4 of those circuits fire at the exact same moment.
Simultaneously?
Yes. In one single clock tick, it calculates x plus speed x, y plus speed y, z plus speed z, and w plus speed w, all at once.
So wait, it does 4 math problems for the price of 1?
Exactly. We just made the computer go 4 times faster.
Right.
And we didn't make the clock faster. We didn't make the electronics more complicated. We just stopped wasting all that empty space on the desk.
That is amazing. That's the CMD revolution. It sounds perfect.
It is great, but
That there is a catch.
of course there is. There is always a catch. What is it?
The computer becomes very, very picky. The CPU is like a librarian who is extremely strict about organization.
Okay.
And this brings us to part 2 of our deep dive, memory alignment.
Memory alignment. That
Yeah.
sounds like arranging books perfectly on a shelf. That is a very, very good comparison. To understand this, we have to look at what memory, or RAM, really looks like.
Okay.
We often think of variables as, these floating bubbles of data, but physically, RAM is just a long straight line of bytes.
Like a ruler.
Yes, exactly like a ruler. Every mark on the ruler is a byte. and every byte has a number. We call this number the address.
So we have address 0, address 1, address 2, address 3, and so on.
Precisely. Now, the notes talk about hexadecimal numbers. That usually scares beginners.
It does. It looks complicated.
Can we explain it simply?
Please.
Of course. Humans count in base 10. We have 10 fingers, so we use the digits 0 through 9. When we get to 10, we need 2 digits to write it.
Right.
Computers, for reasons related to their wiring, they prefer the number 16. So they count in base 16.
Okay.
So they count 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. But then they need single digits for 10, 11, 12, 13, 14, and 15.
So what do they use?
They just use letters from the alphabet. A is 10, B is 11, C is 12, D is 13, E is 14, and F is 15.
So if I see an address like 0x0f in the code, that just means address 15 in our normal counting.
Exactly. It's just a different way of writing down the marks on the ruler.
Got it.
Now, here's the really important part about the CPU. Remember the library. When the CPU goes to the library to get data, it never picks up just one byte.
It doesn't.
No, it uses a scoop.
A scoop.
Imagine a big bucket. The bucket is designed to hold exactly 64 bytes. We call this bucket a cache line.
Okay.
When the CPU needs data, it doesn't just grab the one byte it needs. It fills the whole bucket and brings the entire 64-byte chunk back to the desk.
So even if I only want one tiny number, the CPU grabs 64 bytes worth of stuff.
Yes. And this creates a problem if you are messy. We call this the straddle penalty.
Straddle, like standing with one leg on one side of a line and the other leg on the other side.
Exactly. Imagine your book is sitting on the shelf in the library. Ideally, the book sits nicely inside one bucket. The CPU goes, scoops it up, one trip, fast.
That makes sense. That's the good case.
That's case A, the good case. But what if you place the book badly on the shelf? What if the first half of the book is at the very end of bucket 1, and the second half of the book is at the very beginning of bucket 2?
Then the CPU has to scoop up bucket 1. Then it has to go all the way back and scoop up bucket 2.
Right. It has to make 2 trips to the library.
That's twice as slow.
And then it has to perform surgery. It has to take the 2 halves and carefully glue them together to rebuild the book. All of this takes time. It makes your program run slowly.
Just because I put the data in the wrong spot on the shelf.
Yes. But for SIMD, for our super fast vector math we talked about, it is even worse. It's not just slow. There is a crash rule.
A crash rule? That sounds serious.
It is. The hardware for SIMD is built to be simple and fast. It can't handle messes. It assumes everything is perfectly organized.
And the rule is?
The rule is your data must start at an address that is divisible by 16.
Divisible by 16. So
yeah.
Address 0 is okay.
Yes. 0 divided by 16 is 0. That's fine.
Address 16.
Yes. 16 divided by 16 is 1. Fine. Address 32 is also fine.
What happens if I try to load a vector from, say, address 4 or address 8?
The program crashes.
It itself stops.
Immediately. The computer gives an error called segmentation fault. It's the hardware saying, I physically cannot do what you asked. The wires are not connected to do that.
Wow. So we have to be extremely careful. If we put our data in the wrong place, the game simply dies.
It dies.
So how do we make sure our data is always in the right place? How do we stay safe?
This is where the programming language helps us. We are using a language called Rust, and Rust allows us to control the layout of memory. We use something called a struct.
A struct, is that like a blueprint for our data?
Yes, it's a map. It tells the computer how to arrange things. Let's imagine we want to store our position, X, Y, and Z.
Okay.
Each of those numbers is a 32-bit float, which takes up 4 bytes of space. So X is 4 bytes, Y is 4 bytes, Z is 4 bytes.
What's the total size then?
4 plus 4 plus 4 is 12 bytes.
Okay, our object is 12 bytes big.
Yeah, let's imagine we have 1,000 of these objects. We line them up in memory, one after the other. Object 1 starts at address 0. Is that good?
Yes, 0 is divisible by 16. That's good.
Okay. Object 1 takes up 12 bytes. So where does object 2 start?
It starts right after object 1, so it starts at address 12.
Right. No, wait. Is 12 divisible by 16? No, it isn't.
So what happens when we try to load object 2 into our SIMD register?
It's going to crash the game.
Yes, the second object in our list will crash the entire game.
That is a huge problem. How do we possibly fix that?
We use a technique called padding.
Padding.
We intentionally waste a little bit of space to make everything line up correctly. Remember, our vector could hold 4 numbers. We only had X, Y, and Z. We add that 4th number, W. Even if we don't need it for our math, we add it just to make the object bigger.
So now we have X, Y, Z, and W. That's 4 plus 4 plus 4 plus 4.
That is 16 bytes.
I see.
Now let's look at the memory line again. Object 1 starts at address 0, It is 16 bytes long. So where does object 2 start? It starts at address 16.
Is 16 divisible by 16?
Yeah.
Right. And object 2 is also 16 bytes long. So where does object 3 start?
At address 32, which is also divisible by 16.
Exactly. By making the object a little bigger, we made sure it always fits the grid perfectly. Every object is now safe.
So how do we tell the computer to do this?
In Rust, we give a specific command. It looks a little strange. The command is #reprline.
Okay, that looks like weird code. What does it mean?
Repr is short for representation. It's telling the computer, I want to talk about how this data is represented in physical memory.
In a line?
That is the order. It's a strict command to the computer. It says, never ever put this object at a memory address that is not divisible by 16.
So that one line of code gives us safety from crashes.
Yes, and this is why this kind of programming is so interesting. We are not just writing math equations. We are managing the physical location of electricity inside the memory chips.
That is a great transition. Let's talk more about speaking to the machine. This is part 3 of our outline. The notes say something that really surprised me. They say, the variable is a lie.
Chuckles. Yes. It's a bit dramatic, but it's fundamentally true.
What does that mean?
When you first start learning to code, your teachers use a metaphor. They say, a variable is a box.
Right.
They say, imagine a little cardboard box. Write the name X on the side, then you put the number 5 inside the box.
That is exactly how I visualize it. I have a box named X, and inside that box is the number 5.
Well, in the physical machine, there are no boxes. There are no names. There is only the stack.
The stack? What's that?
Imagine a notebook, or maybe a very tall pile of plates. The CPU has something called a stack pointer. This is like your finger pointing to a specific line in the notebook.
Okay.
When you write code like let X equals 5, 3 things happen physically, not metaphorically, physically.
Let's go through them slowly. Step 1.
Step 1. The stack pointer, the finger moves down one line. It reserves space. It says, this line in the notebook is now being used.
Okay. Space is reserved. Step 2.
Step 2. The CPU writes the number 5 on that line in the notebook.
Right. And step 3.
Step 3. The compiler, the program that reads our code, creates a label in its own internal notes. It says, from now on, whenever the human types the letter X, what they really mean is this specific memory address, like 0i7ff1234.
So X is not a box at all. X is just a nickname for a memory address.
Exactly. It's a convenience for us humans. The machine only knows about addresses.
That changes how I think about it.
Yeah.
The notes also talk a lot about immutability. That is a big word. What does it mean?
Immutable means cannot change.
Cannot change.
In the Rust language, when you create a variable, it is locked by default. You write the number 5 to that spot on the stack. If you try to change it to 6 later in your program, the computer will shout at you. It will give you an error and refuse to continue.
But why? In a game, things change all the time. My health changes, my position changes, my score changes. Why would I want variables that are locked?
It is for safety. Think about a huge, complex game engine. You might have millions of lines of code written by hundreds of different programmers.
Okay.
Imagine you write the code that calculates the physics for an asteroid. You're done with it. The position is correct. But then a totally different part of the code, maybe the sound system or the graphics system, accidentally writes a new number to that asteroid's memory address.
That would be a terrible bug. The asteroid would just teleport for no reason.
Exactly. By making everything read-only by default, we prevent those kinds of accidents. The compiler guarantees that nobody can touch that data unless we give them special permission.
And how do we give that special permission?
We use one simple keyword, mut. It's short for mutable, which means changeable.
So I would write let mut x equals 5.
Correct. That little mut acts as a permission flag. It tells the compiler, I know this data is locked by default, but for this specific variable, I'm allowing it to be changed later.
It really sounds like Rust is very strict. It's like it doesn't trust the programmer.
It is strict. It treats the programmer like they're working in a nuclear power plant. It forces you to follow safety protocols to prevent disasters.
Okay, let's talk about types. The notes say memory is just electricity.
Yes. At the lowest level, a memory cell is just a tiny switch. It is either on N, which we call 1, or O off F, which we call 0.
Right, bits.
Right. So if I give you a sequence of bits, a pattern of ONs and O off Fs, like 010000001, what does that mean?
I have no idea. It's just ones and zeros. It's meaningless.
Exactly. It has no meaning on its own. We need a type to give it meaning. A type is like a lens that we look through to interpret the bits.
Can you give an example?
Sure. If we look at those same bits, 01000001, through the U32 lens, which means unsigned 32-bit integer.
A counting number.
Right, a simple counting number. Those bits represent the number 65. But if we look at those exact same bits through a different lens, the char lens, which means character, they represent the letter A.
Wow. So the electricity in the chip is identical, but the meaning changes completely depending on the type, on the lens we use.
Yes. And if you use the wrong lens, you get garbage. If you try to read a number that was meant to be a character, you just get a nonsense value.
So for physics, what lens do we use?
For physics, we need numbers with decimal points, like 3.14. So we use a type called F32.
F32.
That stands for floating point 32-bit.
How does that work? How can it represent decimal numbers?
It's very clever. It takes the 32 bits and it splits them into 3 separate sections.
Okay.
Section 1 is the sign bit, just 1 bit. Is this number positive or negative?
Yeah.
Section 2 is the exponent. This tells us the size of the number. Is it a huge number, like a billion, or a tiny microscopic number? And section 3 is the mantissa, or the fraction. This gives us the precision, the actual digits.
So it's kind of like scientific notation in math class.
That's exactly what it is. It's a very efficient way to use 32 bits to represent a huge range of numbers, from the distance between stars to the size of an atom.
There's one more type mentioned in the notes that seems important. U size.
Ah, yes. U size. That's the address type.
The address type.
Yes. If you have a 64-bit computer, then U size is 64 bits long. If you had a 32-bit computer, it would be 32 bits long. It is designed to be exactly big enough to hold any memory address on the computer. It's the type we use for pointing to things or for counting how many items are in a list.
Oh, I think I'm starting to get it. We understand the hardware, the memory, the rules of Rust. So now let's open the source code. Let's look at the real thing.
Let's do it.
We are looking at part 4, the code base map. We have a file here from the Titan engine. And to a beginner, looking at code can be, well, scary. It looks like a foreign language.
It does. But we can learn to read it, just like a story. The very first thing you'll probably see in the code are lines that start with 2 slashes.
Yes, I see one here. It says Titan fast key.
Okay, those are comments.
Comments.
The compiler, the program that turns our human-readable code into machine-executable software, it ignores these lines completely. When it sees those 2 slashes, it just skips to the next line.
So who are they for?
They are for humans. The programmers leave notes for each other and for their future selves. In the Titan engine, they use these special tags like Titan FastQ. This helps them search through all their files later. If a programmer wants to find all the code related to physics, they can just search for that tag. It's like putting a little colored sticky note on a page in a book.
That's clever. Okay, the next line I see is use crate.simd something. What is a crate? Is that like the shipping crate we talked about?
Chuckles. Not quite, but it's a good thought. In Rust, a crate is the whole package. It's the box that holds all the code files for a project.
I see.
So crate tells the compiler, start looking from the main top-level folder of this project. Then SIMD tells it. Now, look inside the folder named SIMD. It's just like giving a file path on your computer. C drive, then the users folder, then the documents folder.
Okay, that makes sense. Now look at this line. This seems important. It says pub type backend, default backend. It looks like we're giving something a nickname.
That is exactly what it is. This is a technique called type aliasing.
An alias.
Yes. Imagine we are writing this huge game engine. We might use the word backend thousands of times in our code. Right now, that backend means standard CPU math, which is default backend.
Right.
But technology changes really fast. Maybe next year, a new kind of computer comes out with a much faster way to do math.
So we would want to switch to the new, faster map.
Exactly. Now, if we had written default backend thousands of times, we would have to go and find and replace every single one. It would take days, and we would probably make a mistake.
I see.
But because we use the nickname backend, we only have to change one line in the entire project. We just change this line to type backend and new superfast backend.
And just like that, the whole game engine updates to use the new technology.
Yes, the compiler does all the work for us. It saves a huge amount of time and prevents bugs. It's very smart planning.
It really is.
Yeah.
Okay, now let's go deep. Let's look at the actual object we've been talking about, the SIMVec4. This is part 5. I'm seeing the line. Structs SIMVec4 pub backend. And right above it, there is another one of those strange instructions in brackets. Hashtag rep transparent. We saw rep line before. What does transparent mean here?
This is a really important concept in modern programming. It's called a zero-cost abstraction.
Zero-cost abstraction.
So we are creating a new type called SIMVEC4, and inside it we are holding the raw hardware data, which we call backend. Usually when you wrap something in a container, that container adds a layer. It takes up space.
Right. Think of a gift. If I put a gift in a box, the box itself has weight and takes up space.
Perfect analogy. But hashtag #retransparent is a secret message to the compiler. It says, this wrapper, this SIMVEC4 box, is fake. It's invisible.
Fake.
It tells the compiler, for the human programmer, I want you to treat this like a new safe type. But when you generate the final machine code, I want you to pretend the wrapper does not exist at all.
So it takes up zero extra memory. It has zero cost.
Zero. It is exactly the same size and memory as the raw data it holds. We get the safety and organization of a new type, but with the raw speed of the underlying hardware. It's the best of both worlds.
I also see a line that says hashtag derive, clone, copy, and a few other things. Derive means to come from something. What does it mean here?
Here it means write the code for me.
Yeah, I like that.
In programming, there are a lot of boring, repetitive tasks. For example, how do I make a copy of this object? I could sit here and write code that says, copy bit number 1 to the new location, copy bit number 2.
That sounds terrible.
It is terrible, and it's boring, and you might make a mistake. So instead, we just put derive, copy. This is like telling a little compiler robot, hey, you had to copy things. Please write all that boring code for me in the background.
That is very handy. It automates the boring stuff.
Exactly.
Now let's talk about traits. The code mentions trait SIMD mask. What is a trait?
A trait is a contract. It's a set of promises.
A
Yes. A trait does not tell you what the data is. It doesn't care about the data itself. It tells you what the data can do.
Okay, abilities, not identity.
Precisely. For example, the SIMD mask trait is a contract. It says, any object that wants to call itself a SIMD mask must promise to have a function called any and a function called all.
Any and all, like asking questions.
Yes, exactly. The physics engine needs to ask questions all the time. Did any of the asteroids hit the ship? Or are all of the asteroids still inside the game world? The trait defines a common language for how we ask those questions.
Okay, next concept, inlining. I see the instruction hashtag inline always above almost every single function in this file. Anyway, why is it everywhere?
To understand this, we have to look at the cost of using a function.
A function has a cost.
It does. Imagine you were reading a recipe in a cookbook. You're on step 3. Then the recipe says, for how to properly chop an onion, please see page 50.
Okay, so I have to stop what I'm doing. I have to find the page number. I have to flip all the way to page 50. I read the instructions there. Then I have to remember where I was and flip all the way back to step 3.
That flipping back and forth takes time. In the CPU, we call that jumping. Jumping to a function and then jumping back takes time and energy. And if the function is very, very small, like just adding 2 numbers, the act of jumping can actually take longer than the math itself.
That is so wasteful.
It is. So hashtag inline always is a command. It tells the compiler, do not create a jump, do not make me flip pages. Instead, it says, take the instructions from page 50 and just copy paste them right here into the middle of step 3.
So it literally deletes the function call and just puts the instructions right there inline.
Yes. This makes the final program file a little bit larger because we are copying the same text many times, but it makes the program run much, much faster because the CPU never has to stop and jump around. It just flows straight through the instructions like water.
Okay, we are getting into the really deep details now. This is great. Part 6, specific functions and safety.
Let's do it.
Let's talk about safety again. The code has a function called from slice unaligned, and inside this function there's a block of code marked with the word unsafe. Why is it marked unsafe? That sounds dangerous.
It is dangerous. That's why it's clearly marked. It's loading data from the wild.
The wild.
We are taking a normal, everyday life of numbers, a slice, and we are trying to load it into our special, super fast SIMD register. Now, remember the alignment rule?
Yes, the divisible by 16 crash rule.
This function is special because it knows how to handle data that is not aligned. That's why it's called unaligned. But there is another danger.
What's that?
The length. Our SIMD register needs to hold 4 numbers. What happens if the slice, the list of numbers we're given, only has 3 numbers in it?
Oh, if we try to read the 4th number, it doesn't exist. We'd be reading something else.
Yeah. We would be reading forbidden memory. We might read a password or a piece of another program, or most likely, we would just crash the game. So the code has a special safety check. It says debugassert.slice.lin equals 4.
Okay, what does debugassert do?
It's a safety check that only runs when the programmers are testing the game. It says, check the length of the slice. If it is less than 4, stop everything, panic, and crash the program right now.
Why would you want it to crash?
So the programmer sees it immediately, it crashes and gives them a message saying, you made a mistake right here. This helps them find and fix bugs early.
So what happens in the final game that you buy?
In release mode, the final version of the game, this check is completely removed to make the code as fast as possible. We assume the programmer has already found and fixed all those bugs.
I see a funny word in the code, splat. It says pub, fn splat, vf32, ace self. Is splat a real technical term?
Yes, it is. It's a very common and descriptive term in graphics and physics programming.
What does it do?
Imagine you have one single number, like 5.0, but you need to fill a whole vector of 4 numbers with that same value. So you get 5.0, 5.0, 5.0, 5.0. You take that single number and you splat it across all 4 slots.
Like throwing a tomato at a wall.
That is a perfect visual, yes.
Okay, now we get to the heavy math. I see .3 vec and cross 3. We don't need to learn the exact formulas, but what are these used for in a game?
These are the 2 most important tools in the entire toolbox for 3D math. .3vec is the dot product. It tells us about angles.
The angles.
Are 2 objects facing the same way? Are they facing opposite ways? Are they perpendicular? It's used everywhere, but especially for lighting. If a surface is facing towards the light, the dot product is high and the surface is bright. If it faces away, it's dark.
Then cross 3.
That is the cross product. It's a bit more magical. If you give it 2 directions, it gives you a third direction that is perfectly perpendicular to both of them.
Like, if I have forward and right, it will give me up.
Exactly.
But,
It's used all the time to figure out how objects should rotate and tumble in space.
Now, here is the most impressive part of the source code, I think. The robustness section. The notes talk about a problem with an operation called normalizing. First, what does it mean to normalize a vector?
A vector has 2 parts, a direction and a length or magnitude. Sometimes we only care about the direction. We want the length to be exactly 1. To do that, we divide the vector by its own length.
So vector divided by length.
Correct.
Okay, but what if the object isn't moving? What if its speed is 0, so the length of its velocity vector is 0?
Then we have a problem. We are trying to divide by 0.
In math class, my teacher said you can't do that.
You can't. In computers, trying to divide by 0 creates a monster. It creates a special value called nan. It stands for not a number.
Not a number.
It is a toxic, poisonous value. If you have a nan and you add it to a normal number, the result is also nan. It spreads like a virus. Suddenly, your entire physics simulation is full of nans and all your asteroids disappear into nothing.
So we must, at all costs, prevent dividing by 0.
At all costs.
Usually, in normal code, I would just use an if statement. If length is greater than 0, then divide. Otherwise, do something else.
Correct. But remember SIMD. We are calculating 4 things in 4 lanes all at once. What if lane 1 has a length of 0, but lane 2 has a length of 5? We can't easily use an if statement. An if is a branch. It means the CPU has to stop and choose one of 2 paths. Branching is very slow. We want our code to flow like water without any stops or choices.
So how does the Titan engine solve this without an if statement? This is the normalize 3 function. Let's walk through it very, very slowly.
It uses a very clever trick with a mask and a blend. Here is the recipe. Step 1, calculate the length squared. We call it len square.
Go.
Step 2, create a mask. The computer asks a question for each of the 4 lanes. Is length extremely close to 0? This gives us a mask of true-false answers like true, false, false, true.
Okay, so now we have a list. We know which lanes are bad because they are 0 and which ones are good.
Exactly. Now, step 3, the blend trick. This is the clever part. We create a new temporary value. We tell the computer, look at the mask. For every lane that was true, the bad ones, I want you to replace the value with the number 1.0. For every lane that was false, the good ones, I want you to keep the real length.
Wait, why 1.0? 1.0 is not the real length for the bad ones. That's a wrong number.
It is a wrong number, but it's a safe number. We are preparing to do a division. Dividing by the real value, 0, would create an an. But dividing by 1.0 is perfectly safe. It doesn't crash.
So you are temporarily faking the data for the bad lanes to avoid a crash.
Precisely. So now we have a list of numbers. The good ones are real. The bad ones are fake 1.0s. Now, step 4. We do the division. We calculate the result. Since all the zeros were replaced by 1s, no crash happens. No nans are created.
But wait, The result for the bad lanes is now wrong.
Right.
We divided by 1.0, but the real length was 0. The answer for those lanes is complete garbage.
It is complete garbage for those specific bad lanes, and the computer knows this. So, step 5, the final blend. We look at our original mask one last time. We tell the computer, if the mask for a lane was true, meaning it was a bad one, I want you to throw away the garbage result you just calculated. Replace it with a safe fallback value, like a vector of all zeros. If the mask was false, then keep the correct calculated result.
That is incredibly clever. Let me see if I have this right. You check which inputs are dangerous. You fake the dangerous inputs to make them safe. You do the math on everything. And then at the very end, you throw away the results that came from the fake data and replace them with a safe answer.
That's it.
And this all happens without any if statements, no branching.
None at all. It's all just a sequence of math operations. Compare, blend, math, blend. It flows through the CPU pipeline smoothly without ever stopping. This is how you get rock-solid, stable physics that never crashes without slowing down the game.
We have covered so much ground today. This has been amazing. Let's look back at our journey.
Okay.
We started with that super strict 16 millisecond time limit. From there, we went all the way down to the hardware, the desk and the library shelves.
We visualized the scoop of memory, the cache line. We saw how the rigid grid of memory alignment forces us to add padding to our data structures just to stop the game from crashing.
We learned that a language like Rust lets us speak directly to the machine, managing the stack and using types as a lens to interpret the raw electricity.
And finally, we saw the incredible math logic, those blend tricks that programmers use to keep the game safe from errors like dividing by 0.
It really is a journey from this abstract idea of I want to move a rock on screen all the way down to the physical reality of electricity needs to move through these specific silicon paths.
It is.
So what does this all mean for our listener? Why should they care about all this SIMD and alignment and blending?
Because this is how all modern high-performance computing works. We are reaching the physical limit of how fast a single CPU brain can think. The clock speeds aren't getting much faster.
Right.
To get more performance now, we have to go wide. We have to do more things at the same time. SIMD is the first and most fundamental step of learning to think wide.
Instead of doing one thing very fast, you do 4 things at the same time, a little slower.
Precisely. And this idea applies to everything now. Artificial intelligence, processing video, analyzing big data. They all rely on this vector approach.
I have a final provocative thought for you then, a question for our listener to think about.
Okay.
We spent all this time optimizing the math, saving tiny nanoseconds with inline and SIMD blend tricks. But you said earlier that memory, the RAM, is slow. The library is far away.
It is.
As computers get more and more cores, not just 4 SIMD lanes, but 16 cores, 32 cores, 128 cores, will we start worrying so much about the math?
That is the big question in computer science right now. Many experts believe that compute, the math part, is no longer the main problem. It's not the bottleneck.
What is?
The bottleneck is data movement. It's feeding the beast. If you had a brand new 64-core CPU, but you can't pull books from the library fast enough to keep all 64 of those workers busy, then most of your expensive cores are just sitting there idle, waiting for data.
So the future of high-performance programming might not be about writing faster math equations.
It might be entirely about how you organize your memory, how you lay out your data on the shelves in the library so you can scoop it up as efficiently as possible.
So being a better librarian might become more important than being a better calculator.
That's a perfect way to put it. Alignment, cache lines, prefetching data before you even need it. That is the future.
Well, on that note, I think we're going to sign off.
Yeah.
To our listener who asked for simple English,
Yeah.
we really hope this was clear. We hope the pace was good for you.
We hope it helped.
Take some time to review the concepts of alignment and inlining again. I feel like those are the real keys to unlocking the hidden speed of your computer.
They really are. Thank you for listening. Keep learning.